The power of large language models has never really been in question. But we are starting today with a question that, well, must be answered for true global AI adoption. What is the cost?
That's the critical barrier, isn't it? The universal one.
Yeah.
LLMs are these magnificent computational machines, truly, but deploying them, especially on a mass scale or, in resource-limited environments.
Yeah, the demands are huge.
Exactly. Astronomical energy, enormous memory requirements, and often needing that specialized, expensive hardware. It pretty much means the best AI often stays locked behind massive cloud services.
Okay, so today we are diving deep into a report that claims to, well, maybe shatter that barrier. We're talking about BitNet b1.58 2b4t. Now, if those technical numbers sound a bit dry,
Oh.
the implication is definitely not. This is the first widely available open source 1-bit large language model at that crucial 2 billion parameter scale. And it's trained on a staggering 4 trillion tokens.
Right. And our goal in this deep dive is really to unpack the core claim, the revolutionary idea at the heart of this research. That they've achieved performance that's comparable, really comparable, to leading full precision LLMs of a similar size. But, and this is the key part, with a tiny fraction of the memory, energy, and latency needed.
That sounds like, well, the definition of democratizing advanced AI, if it holds up.
Precisely.
Okay, let's frame the problem first, maybe for you listening. We're deep into the age of open models now, right?
Yeah.
They're driving innovation everywhere, coding, complex text analysis, reasoning.
Absolutely. It's an exciting time.
But if you actually want to run one of those amazing models on, say, a standard server in your company, or maybe a laptop, or even an edge device for real-time applications, a model needing multiple gigabytes of just RAM, let alone specialized processors, often just isn't practical. The size and the speed requirements become real blockers.
And that's exactly why this one-bit paradigm is so necessary, potentially so game-changing. We're moving beyond standard quantization techniques, 8-bit, 4-bit,
Right.
into the extreme end of things.
Okay, define extreme. What does 1-bit actually mean here?
It means constraining the model's weights and activations, the numbers the model uses, to the simplest possible values. Often it's just binary, like -1 and +1, or maybe ternary, -1, 0, and +1.
Okay, so you force this really extreme constraint. What's the immediate, tangible benefit? What does that do for the deployment cost?
That's all about efficiency, spatial, and temporal, purely. If you go from, say, 16-bit floating point numbers down to essentially 1 or maybe 1.58 bits per weight, like in this paper,
Right.
the storage space just shrinks exponentially. I mean, we're talking about models that could be smaller memory-wise than a high-resolution photo on your phone.
Wow, okay.
And plus, these low-bit constraints let us swap that complex, energy-hungry floating point math for highly efficient bit-wise computations, simple logic operations. That drastically accelerates the actual processing speed, the latency.
But hang on, previous attempts at this level of extreme quantization, even going down to 4-bit, often seem to fall apart. Performance would degrade significantly, right? We hear about brittle performance a lot. Why did those earlier 1-bit efforts struggle so much?
Yeah, they typically struggled because they either lacked scale or they were trying to kind of fix a fundamental problem after the fact. We saw two common pitfalls, really.
Okay.
First, there was post-training quantization, or PTQ. That's where you take a massive, fully trained, high-precision model like 16-bit, and you try to crush those weights down to 1 or 2 bits after all the training is done.
Ah, okay. Trying to retrofit it.
Exactly. And the report confirms this. It often causes, and I quote, significant performance degradation. Why? Because the model was never actually trained to operate in that extremely constrained numerical space.
Right. It's like you can't really teach an old dog new super efficient tricks without some serious side effects.
Precisely. That's a good analogy. The second pitfall was seeing native 1-bit models, like Errl BitNet 1B was one mentioned. These were trained efficiently from scratch using low bits, which is good, but they were often trained at too small a scale, maybe 1 billion parameters or less. They simply couldn't match the general reasoning or the broad knowledge capabilities of the larger full precision models we rely on.
Got it. So too small to be truly useful for complex tasks.
Exactly. And this is where BitNet b1.58 claims to bridge that gap. It's native training built for low bit from the start at scale, that's the 2B parameters part, with extreme quantization. It aims to fundamentally change that trade-off between performance and efficiency.
Okay, let's unpack the architecture then. If this is a native model, they must have had to really rebuild the foundational structure, the transformer model itself, to handle these ultra-low bit weights effectively. What's the core innovation? What makes this performance possible when you're using less than 2 bits per weight?
Right. The secret sauce, as they say, is replacing the standard full precision linear layers. Those are the components doing the bulk of the heavy computational lifting in a transformer.
Hmm.
They replace them with custom BitLinear layers. The whole design is engineered specifically for stability when you're working with these very, very low bit numbers.
Okay, you mentioned this W1.58A8 scheme earlier. Can you break that down for us? How can the weights be almost 1 bit, yet the data flowing through the model, the activations, still needs 8 bits? That sounds like a carefully managed compromise.
It absolutely is. It's a critical balancing act between getting maximum efficiency and maintaining enough signal quality.
Right.
So the weights themselves, the parameters the model learns, are quantized down to 1.58 bits.
Yeah.
They use an absolute mean or abs mean quantization strategy. It cleverly maps the original weights to just 3 possible values, -1, 0, or +1.
Ternary.
Exactly, ternary. And it's that ternary mapping, needing slightly more than 1 bit to represent 3 states, that gives it the 1.58-bit designation. It's a mathematical representation of the information needed.
Makes sense. So why 8 bits for the activations then? Why not quantize those down extremely too?
Because the activations, that's the intermediate data flowing between the layers during computation,
Hmm.
they need enough fidelity, enough precision to maintain the integrity of the information as it processes. If you squash those down too much as well, the signal gets lost and performance collapses.
Ah, okay.
So they quantize the activations to 8-bit integers using a different strategy,
Yep.
absolute maximum or abs max applied per token. This W1.58A8 scheme, 1.58-bit weights, 8-bit activations, seems to be the sweet spot they found.
So the storage is incredibly efficient because the weights are ternary, super small, but the actual computation inside has enough, let's say, breathing room because the intermediate data is still 8-bit. That makes a lot of sense as a compromise.
It does. And achieving stability with this setup required some additional architectural tricks, too. Highly quantized models are inherently a bit unstable, numerically speaking, so you need every trick in the book to prevent performance just falling off a cliff.
Like what? What else did they change?
Well, for instance, they incorporated Selwyn normalization, which is known to help stabilize training in some contexts. And critically, instead of using the very common SWIGLU activation function you see in many LLMs,
Yeah, that's everywhere now.
right, they chose squared ReLU, or ReLU squared, basically. The paper suggests this was motivated by its potential to improve sparsity and maintain stability, specifically when working with these ternary weights.
Interesting choice.
And another key thing, they completely removed all bias terms from the linear layers and the normalization layers. No biases anywhere.
Really? Why?
It's a design choice that's consistent with some other successful but known to be very challenging to train architectures like Llama, for example. Removing biases can sometimes simplify the optimization landscape, especially in these low-bit regimes.
Wow. Okay, so custom layers, specific activation functions, no biases. This sounds like the training process itself must have been, well, maybe a nightmare to get right. How did they manage that massive 4 trillion token training corpus while optimizing for this highly constrained, maybe fragile environment?
Yeah, the training was clearly meticulous. They broke it down into 3 distinct phases. First was pre-training. On that huge 4T token corpus, they used a 2-stage learning rate schedule there.
Okay, 2 stages.
Yep. Stage 1 was faster, kind of getting the model broadly grounded, learning the basics from the massive data set. Then stage 2 was what they called a cool-down phase. Yeah, they significantly lowered the learning rate and focused exclusively on higher quality, curated data. They specifically mentioned sources like FineWeb EDU. So this 2-stage approach allowed for aggressive foundational learning first, followed by a much more careful refinement phase using premium content to really solidify the knowledge.
Right, learn broadly, then refine carefully. Makes sense. And once the model had its foundational knowledge from those 4 trillion tokens, they moved into the alignment phases, making it follow instructions and be helpful.
Exactly. First up was supervised fine-tuning, or SFT. They used diverse conversational and reasoning data sets, mentioning things like WildChat and Slamorca, to teach it how to follow instructions properly. And they found a really interesting optimization here during SFT. Instead of averaging the loss function, the error signal, across all the tokens in a batch, which is standard practice,
Right.
they summed it instead, just summed up the errors. And they found that this small change in how they aggregated the loss actually led empirically to better convergence, better performance in the SFT phase for this specific architecture.
That is a great example, isn't it, of the kind of non-intuitive tweaking and optimization that's probably required when you're pushing the physical limits of numerical precision like this.
Absolutely. Every little detail matters. Then finally, they finished the training process with direct preference optimization, or DPO.
Ah, DPO instead of RLHF.
Right. Using alignment data, like ultrafeedback. DPO is known to be significantly more efficient computationally than traditional reinforcement learning from human feedback. So it allowed them to rapidly align the model with human preferences for safety and helpfulness,
Mhm.
kind of completing the package without a massive extra training stage.
Okay. The theory sounds solid, the architecture seems carefully tailored, the training was meticulous and optimized. But we need to see the data, right? What actually happens when they pit BitNet b1.58 against its full precision competitors? Does it stack up?
Well, this is where the paper really stops being just theoretical research and starts looking potentially revolutionary. The efficiency gains they report are stunning, especially compared to other full precision models in that sort of 1 billion to 3 billion parameter range.
Okay, let's anchor this with the memory footprint, because that's often the absolute moment of truth for deployment, especially on edge devices.
Right, so the non-embedding memory footprint that's the core model size for this 2 billion parameter BitNet B1.58 model is reported as only zero point 0.4 gigabytes.
0.4.
0.4 GB. Yeah. Think about that for a second. Mini CPM, another 2B parameter model they compared against, sits at 4.8 gigab. Quen 2.5, a strong 1.5B parameter model, is 2.6 gigab.
That's not just a reduction, it's an order of magnitude shift, isn't it?
It really is. It makes the model potentially viable for running directly on a consumer laptop, maybe even a Raspberry Pi eventually, without needing specialized cloud infrastructure.
Wow. 0.4 GB, that's smaller than the operating system on my phone, probably.
When you first saw that number in the source material, did you have to, double check the decimal point?
Huh. It definitely makes you look twice. It's the kind of number that really proves the potential of the concept.
Yeah.
But, okay, efficiency isn't just about size, it also has to mean speed, right? Latency.
Yeah, absolutely. Especially for real-time stuff.
So they did CPU testing, which is crucial for accessibility. On CPU, BitNet B1.58 achieved 29 milliseconds latency per token generated.
29 Ms. How does that compare? Compares really favorably. Llama 3.21b was around 48 meters on their setup, and Mini CBM2B was much slower at 124 meters. So significantly faster inference on standard hardware.
Okay, tiny memory, fast on CPU. What about energy?
That speed, combined with the low memory access and simpler computations, results in incredible energy savings. Their estimated energy consumption is just 0.028 joules per token.
0.028.
Yep. Contrast that with something like Llama 3.2's estimate of 0.258 joules. It's a huge difference. We're talking about significantly greener AI, much more sustainable to run at scale.
Okay, so the efficiency claims seem, well, dramatic and proven by their numbers, but the core challenge always remains: performance parity.
Did they actually achieve their goal of performing just as well as the larger full precision models? Or did they sacrifice capability for that efficiency?
This is perhaps the most compelling aspect of the paper. Across a broad suite of 11 standard benchmarks covering reasoning, language understanding, common sense, math.
The usual suspects, MLU, hella swag. Exactly, all those. The model achieves an average score across these benchmarks of 54.19.
Okay, 54.19. How good is that?
Well, the key comparison is against the top-performing full-precision model in their comparison set, which was Quen 2.5 1.5b. That model scored 55.23 on average.
So, almost identical performance.
Pretty much, yeah. Within the noise, almost. This confirms it's not just efficient for, simple text completion. It holds its own on complex tasks.
And were there any specific areas where it really stood out?
Yes, crucially, they highlighted specific wins. BitNet B1.58 actually achieved the best performance among all the models they compared, including the full precision ones, in key reasoning areas. Specifically, ARC Challenge, a science question benchmark, and especially the mathematical reasoning benchmark, GSM-8K.
Math reasoning. That's usually tough for smaller, compressed models. It scored 58.38 on GSM-8K, which was the top score. This strong performance in math is really important because that's traditionally a weak spot for highly compressed models. It demonstrates that this native 1.58-bit training process managed to retain complex reasoning capability, not just pattern matching.
Okay, and this capability, this native performance, how does it contrast with those older methods we talked about, like post-training quantization, compressing after training?
Right, they did that direct comparison too. They took the Quen 2.5 1.5b model and quantized it down to 4-bit precision using standard methods like GPTQ and AEWQ. These are kind of the state-of-the-art for after-the-fact compression right now.
And the results?
The performance difference really validates the native training approach they took. While INT4-PTQ did reduce the memory footprint of Qwen 2.5 down to about 0.7 GB.
Still almost double BitNet's 0.4 GB.
Exactly. But more critically, the performance dropped. The INT4 quantized versions scored around 51 or 52 on the average benchmark score. BitNet b1.58 at 0.4 GB maintained a stronger average performance of 55.01 in that specific comparison table. So, native training is just superior for achieving this extreme level of efficiency without sacrificing the smarts.
That's what their data strongly suggests, yes.
Yeah.
Training it low bit from the ground up seems key.
Okay, let's shift gears slightly to practical deployment. If this model uses these unusual 1.58-bit weights and 8-bit activations, it's working with a numerical format that standard hardware, like GPUs, aren't really designed to handle natively, right? What was the hurdle for actually implementing and running this thing?
That's the main challenge right now for wider adoption. Commodity GPU hardware and the standard deep learning libraries like PyTorch or TensorFlow, they lack optimized kernels, the low-level computation routines for this specific W1.58A8 mixed precision format.
So GPUs are built for standard sizes, like 8-bit, 16-bit, 32-bit math operations.
Precisely. They aren't optimized out of the box for doing massive calculations using 1-bit or 1.58-bit ternary values efficiently.
So just to get the results for the paper, they had to build a custom solution to actually run it efficiently and prove that the theoretical gains were real in practice.
It's exactly right. For GPU inference, they created a custom CUDA kernel. The core issue is that these 1.58-bit ternary weights, well, you can't store them efficiently in standard GPU memory slots, which are usually designed for chunks of 8 bits or larger.
Right, a 1.58-bit weight doesn't fit neatly.
Doesn't fit neatly at all. So they adopted what they call a pack, store, load, unpack, compute strategy.
Okay, pack, store, load, unpack, compute. Break that down. Does that mean, like, the individual weights are too small for the standard memory slot, so they're taking, say, 4 of these tiny ternary weights and bundling them together into one package, maybe a single 8-bit integer, just to trick the GPU's memory system into reading them efficiently?
That's a perfect analogy for it, yes.
Right.
They pack 4 ternary values into one standard 8-bit integer in memory. This minimizes the memory bandwidth usage during inference, which is often the biggest bottleneck. Then inside the custom kernel, they unpack them just before doing the actual computation.
Clever workaround. Maximizing the use of the existing hardware structure, even if it's not ideal.
Exactly. It shows it can be done efficiently on current hardware, even if it requires custom code.
And for maximum accessibility, knowing that most potential users aren't running custom CUDA kernels, did they provide a solution for simpler CPU-only environments?
Yes, absolutely. Recognizing the deployment on laptops, smaller servers, maybe edge devices is a primary goal here.
Yeah.
They also released the open source bitnet.cpp C++ library.
Ah, bitnet.cpp.
Yep. This serves as the official reference implementation. It's designed to ensure efficient execution on standard CPU architectures using C++men. This really proves that these 1-bit models can run efficiently in many places, even without needing exotic or custom hardware accelerators. It brings it closer to reality for many developers.
Okay, so summing up the core achievement here, BitNet b1.58 to b4t really feels like a powerful proof of concept, doesn't it? It seems to prove that high-performance LLMs can be trained natively at a reasonable scale using this extreme quantization.
I think that's fair, yes. A strong proof of concept.
And if that holds true in scales, it could fundamentally change the economics of AI, making advanced capabilities far cheaper, far more sustainable, and ultimately more globally deployable.
Absolutely. And the research avenues that spring directly from this are wide open now. The team themselves mentioned they're already looking at scaling this method up way up to much larger models. Think 7 billion, 13 billion parameters and beyond.
To see if this performance parity holds at truly massive scale.
Exactly. Does the efficiency benefit continue to scale linearly or better? They also want to extend the maximum sequence length the model can handle, which is important for complex, long-context reasoning tasks. And of course, exploring multilingual capabilities and even multimodal integration, mixing text and images, perhaps.
It really sounds like maybe for the first time with these extreme quantization methods, the limiting factor isn't necessarily the software algorithms or the mathematical theory anymore, but maybe the actual silicon, the hardware we currently use.
That is arguably the ultimate takeaway, the most forward-looking point from this research. The BitNet team notes it explicitly in the paper. The full potential of these 1-bit models is currently being held back, constrained, because commodity GPU hardware just isn't optimized for these kinds of low-bit operations.
Right. We're running these incredibly efficient algorithms on general-purpose machines that were designed primarily for traditional floating point math.
Exactly. So, okay, here is the final provocative thought for you, the listener, to consider.
Yeah.
If this model, BitNet b1.58, is achieving state-of-the-art efficiency and near performance parity today, running on what is essentially suboptimal general-purpose hardware,
Mm-hmm.
what kind of leap in speed, in energy efficiency, maybe even in capability, could you expect when future chips, future hardware accelerators, are custom-built specifically from the ground up to support these one-bit or ternary computations natively?
Wow.
The potential for maybe orders of magnitude improvements down the line?
Yeah.
It's truly staggering to think about. That's where this could really lead.